ahead to get to this slide. I'm going to skip back. Yeah, I should have reloaded this because it was coming in 2 slides at a time. So let's go back and see what we missed. Real quickly, we need to get to electron activities. One thing, I want you to have this out for 2 reasons. This and this. This is one of the slides in this module, electronegativities. So it is, yeah, we'll see what these numbers are and how to use them here in a minute, and it will be provided to you on an exam. Am I going too fast? I don't want to overwhelm you. I want you to stick with me, okay? It's like if your cross-country coach went out and jogged with you and left you in the dust. I don't want to leave you in the dust. We want to all run this track together. All right? I'm not trying to leave you in the dust. All right, so again, this is a little bit review. I'll have to kind of blow these up. Like I said, this loaded in a little oddly. The key thing is we're talking about ionic bonding, transfer of electrons. You form ions when you transfer electrons. That's an ionic bond. Covalent bonds, sharing of electrons. You share electrons. You don't form ions. The 2 atoms in the bond are sharing electrons, and they're not ions. They're covalently bound to one another. And then think of this as a subset of covalent bonds, polar covalent bonds. That's where 2 atoms do share electrons, but they don't share them equally. I always try to think of family. I try to think of family relationships. When you're 16, you got your driver's license. Did you share the car equally with your dad? Your dad, if he needed the car, he got the car, right? If you need a car all the time, then work, make some money, and you can have your own car. But for right now, we're going to share this car unequally. When you need a car, let me know, and if I don't need it, you can use it, right? That's polar covalent bond. There is one car, it is being shared, but there is a priority on who gets it. So that's a polar covalent bond, unequally shared electron pairs. Oh, did I skip over the slide underneath it? Chemical bondings. Oh, this is worth remembering. The ionic bond, generally speaking, you're going to get an ionic bond when you have a metal reacting with a nonmetal. All right? So if you got rubidium reacting with fluorine, you're not going to get a covalent bond. You're not going to get shared electrons. The rubidium is going to lose the electron and fluorine is going to gain it. So generally speaking, if you have a metal reacting with a nonmetal up here in this corner here, you're going to get an ionic bond. Covalent bonds form when you have a nonmetal reacting with another, with an element close to it, carbon monoxide, carbon dioxide, nitrogen oxide, dinitrogen or pentanitrogen dioxide, sulfur dioxide, sulfur trioxide. Okay? When these things react together, they form covalent bonds and they share electrons. A nonmetal with a nonmetal, or when you actually have the atom react with another atom of itself. F2, fluorine 2, chlorine 2, bromine 2, iodine 2. They are exactly equal atoms and they don't transfer electrons, they share them between them. So that's a good thing to remember. So here's a covalent bond, pure sharing of electrons. You have one hydrogen, you have another hydrogen. They each have one electron. They want two. They want to be like helium. And so they say, I'll share my electron with you if you share your electron with me. And they form a covalent bond. So sometimes we use in Lewis dot structures, we just show the electrons as dots, but we could represent right here, we're converting those two shared electrons into what we have right there is a single covalent bond. So whenever you see a line between two atoms, it's representing two electrons. So for example, you could have when you see two lines, that's a double. This is a double covalent bond. It's 4 electrons being shared between those two atoms. And there's going to be something else on here, but for right now, just focusing on those two right there, that's a double covalent bond. Okay, let's just answer this question real quickly here. How many hydrogens does nitrogen, oxygen, and fluorine bond to, and why? Now let's go to, look at where these are, nitrogen, oxygen, and fluorine. And very first thing I want you to think about is what would be the Lewis dot structure of nitrogen. This is a little bit review, but not from very long ago. Remember, in the Lewis dot formula for nitrogen, what are the only dots we put on the valence electrons? So how many valence electrons does nitrogen have? 5. It's group 5A. Look at your periodic table. You got a 5A above there. I keep saying I'm going to change numbers on this table. It doesn't have 5A, but that it is 5A. So it has 5. Oxygen, how many valence electrons?
6.
Fluorine, 7. 7A. Okay? Okay. So we're armed with that. Before we even start to try to answer this question, let's get there. How many electrons are in the outermost energy level for these elements? Nitrogen's 5, oxygen's 6, fluorine's 7. I can pick that right up off of the periodic table from the group it's in. How many valence electrons it has. Number 2, keep in mind there's something called the octet rule. Each one of these elements want to be like what?
The nearest noble gas.
Which is? Neon. Which has how many? 8. So neon looks like this. All right, so what they're saying over here is if nitrogen were to react with hydrogen and share electrons between nitrogen and hydrogen, how many hydrogens would it have to react with? 3. Because here's what hydrogen looks like. You with me? So I'm going to put a hydrogen right there. I'm going to put a hydrogen right there. And I'm going to put a hydrogen right there. And what that would correspond to now is this. And that would be the Lewis dot structure for a compound that has the formula NH3. Anybody know what NH3 is? Ammonia. That's the compound ammonia. So you go home, you pick up a Windex bottle, squirt it on the window, because no one else around the house will do windows. So you're going to do windows. You're spraying ammonia and water on your windows with a little blue dye in it. Why? Because if the bottle was clear and colorless, you'd think, I think it looks just like water. So they put a little blue dye in there so it makes you look like you're buying something. Ammonia is not blue. It's colorless. All right? Put a little blue dye in there. You go, wow. You go get your windshield, your windshield washer fluid. It's blue. I think that has ammonia in it. I'm sure it does. Okay, that's ammonia. How many hydrogens does oxygen need to share electrons with? 2. And why are we doing this? Because the octet rule is telling us that element, oxygen, wants an octet of electrons around it. And so we would convert this to this. What I'm doing is where there is a covalent bond, I'm putting a line. And where there is an unpaired electrons, pair of unshared electrons, I'm putting the dots. So I still can go here. 2, 4, 6, 8. 2, 4, 6, 8. There's 8 electrons around there. And this is H2O. And we know what H2O is. Water. And I don't care if it's in the typhoon that went across the Pacific or Florence coming into North Carolina, it's always H2O. And now you know why oxygen always does that. It just doesn't kind of, I mean, this is why it always does that. Oxygen wants 2 hydrogens, doesn't want 3, doesn't want a 3rd hydrogen there. Fluorine, how many hydrogens? 1. And so you would get a compound like this. Now I'm using this just to show you the octet. And this is just hydrogen fluoride. You put it in water and it's going to form hydrofluoric acid. Hydrofluoric acid, which is a pretty nasty acid. Have you had experience with hydrofluoric acid?
No, just in the movies.
In the movies?
Yeah, they use hydrofluoric acid.
When did they use that in the movies?
I think they use it to chop off the body. No, that's hydro something else.
Chloric acid?
Hydrochloric acid, that's what it was.
Yeah.
Hydrofluoric.
Yeah, both of them are bad. They're both bad acids. Hydrofluoric is worse. So there's hydrofluoric. But this also shows you why hydrochloric is going to be the same thing. Why? Because chlorine is also group 7A. It has the exact same electron dot formula as fluorine, 7 dots around it. And so it wants 1 hydrogen, so that's hydrochloric. And then we will later just write these like that, HCl, HF, and this is hydrogen fluoride. It's a gas. And if you bubble that gas into water, it forms hydrofluoric acid. Very strong acid. And it's a bad one because you get it on you and it's hard to get it off. It wants to go down into the skin and into the bone. It actually wants to go into the bone. So I don't even know how they treat hydrofluoric acid burns, but hydrochloric acid burns, you wash with water and water and water and water and it'll wash it off.
Quick question too. So when we're doing those, now I see that for the first one, for ammonia, we have NH3. But when we go all the way to fluoride hydrogen, it's HF. So it kind of switched now. Does that matter or no? Could I put FH or HF, or does that matter whatsoever?
I grabbed the bottle in there. I think it's our magnesium chloride bottle. Or there was a bottle there. There was another bottle where they were writing the chloride first and the magnesium second, which makes me question their chemical experience.
Right.
You're usually putting the positive, what would be the more positive part of the molecule first, and the negative one second.
Okay.
In ionic compounds, we're going to always write the positive ion first and the negative ion second.
Okay.
So that's what you're seeing. See, there's your positive ion, there's your negative ion.
Well,
Positive, negative.
I understand that.
Right.
That. But when we went to like the fluoride hydrogen.
Some of these are just by convention. This is how we do ammonia.
Yeah. Well, no. I understand that part. I understand that. But like when we go to like fluoride hydrogen, see how they're just flipped, where you have
this here, and I put it here.
Now it's
I could have. Right.
Yes.
Yeah, because the fluorine will always be the second one in the formula.
Okay.
Because it tends to be more negative. Even though it's not an ion, we'll talk about the polar covalent bond, it is drawing these electrons towards it more so than the hydrogen. It's got a stronger tug. We'll see that. But yeah, hydrogen is generally ahead. Now let me show you an exception. You'll see things like HF, HCl, HBr, HI. These are all hydrofluoric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid. Hydrogen's very often H2O, very often in the front. But if I have hydrogen react with one of these metals, I throw it behind the metal. Now, what's going on there? This is a hydride, and it tends to be negative. The potassium tends to be positive. So we throw the hydrogen behind the metal. This is very rare, so don't worry too much about this. This is a hydride. So would you ever see the H at the end of the formula? Yes, on a few occasions, but you're generally going to always see H leading. And then, of course, we got this ammonia as the other exception.
Yeah, that's why. Why is H in?
Yeah, that's kind of an odd one. That's just the way we do ammonia.
Okay.
All right. Good question. All right. Here's covalent bonds. Diatomic elements are going to form covalent bonds. They're going to equally share the electrons. Why? The two atoms in the bond, if it's hydrogen, looks like this. If it's fluorine, it looks like this. Chlorine looks like this. The two atoms on the two sides of the covalent bond are identical. These are identical twins. Okay? Getting back to the family. There is complete equal sharing of the electrons between those atoms. Okay, now, there can be unequal sharing. You can have a covalent bond between two atoms of two different elements, hydrogen and chlorine here, and form a polar covalent bond. Here's where we're talking about a polar covalent bond. Now I want to get into electronegativities and a kind of a rule of thumb for deciding whether the bond is going to be equal sharing or close to it, when it's going to be unequal enough that the bond is going to have a polar nature to it, and when is it going to be ionic. So to understand that, you have to first understand what this table is telling us. In the previous chapter, I talked about ionization energies, electron affinities, and they were experimentally determined numbers. Go in and do an experiment, and you could measure the ionization potential, ionization energy of oxygen or fluorine or any element. This is a relative table that was put together looking at all the different behaviors that they knew about every one of these elements and rating them according to the strength with which they attracted electrons. So you see electronegativity, the ability of an atom to attract electrons in a chemical bond. Where do you find the highest number on that table? What's the highest number? Fluorine. So the highest number here is 4. Fluorine. So what that is saying is that fluorine, as you would compare it to any other element in the table, has the strongest attraction for electrons. That kind of goes along with what we said about fluorine. It's got 7 valence electrons. It wants 8. It has a tendency to gain an electron. Well, it has the strongest tendency to gain an electron than any other element in the periodic table. If it comes into competition with any other element in the periodic table, and there's going to be electrons involved, the electrons are going to be drawn to the fluorine stronger than any other element. You follow me? Okay, where's the lowest number? Francium, way down here. All right, so down in this corner, and notice 4, 3.5, 3.0, 3.0, 2.5. The big numbers are up here. Now, we've left out a group here, right? We've left out the noble gases. So don't think you're looking at a periodic table. This is a table of electronegativities laid out in the pattern of a periodic table. But this is not an atomic number. It's an electronegativity. The only thing we would use this number for is to kind of predict behavior, chemical behavior, and who is going to get the electron in a chemical reaction. So big numbers, 2.5, 2.8, 2.5 are up here, non-metals, they tend to gain electrons. Low numbers, 0.8, 0.7, 0.7, 0.9, 0.9. Low numbers are down here. These are your most active metals. These elements have the strongest tendency to get rid of an electron. Give it up an electron. So what are we looking at here? The ability to attract electrons. So francium has the least ability to attract an electron of any other element on the table. You with me?
So it's never going to gain one? It's always going to lose one?
Right. It's always going to lose one. No matter what it reacts with. Even if it reacts with cesium right above it. Well, they're both 0.7. But francium would still give up the electron and cesium would get it. They would form a metal bond, not a ionic covalent. So let's see how we use this. Okay, so right below here, I've got this slide right here. And I'm sorry, I gotta clean these up a little bit. What's that say? What's that say underneath there? The greatest difference in electronegativity between two atoms, the greater the difference, the greater the polarity of a bond. So when we talk about difference, think of it about this. This is kind of a little, later on we will talk about difference in energy, but here we're going to use E for electronegativity. E. So the difference in electronegativity. Now look at the scale goes up to 3.3. Let me tell you why. We have francium. Let's consider francium fluoride. what if a compound formed between francium and fluorine? It's francium fluoride. What would be the difference in electronegativity? Well, fluorine has what? What's its electronegativity? 4. What is francium?
0.7.
So when I say the delta E, I'm just saying what is the difference between those two numbers?
3.3.
All right? And so that's why this scale ends at 3.3. Why does it end at 3.3? Well, I've just picked out the one with the highest electronegativity and reacting with the one that has the lowest electronegativity. And the biggest difference I can get is 3.3. So that fixes one end of the scale. And this is ionic. And francium fluoride is as ionic a compound as you can get. The electron transfers from francium to fluorine, and forms the fluoride ion. There isn't anything more ionic than that. Follow me? Because I can make francium chloride. That's going to be ionic also, but it's not going to be more ionic than francium fluoride. All right. So now, let's go down to the other end here. We've got that end fixed. What has a delta E of 0? Give me an example of a molecule that has a delta E of 0. Two hydrogens. A diatomic molecule. Any diatomic molecule. 2 hydrogens, 2 oxygens, 2 nitrogens. Why? You're going to take hydrogen is 2.1 minus 2.1 is 0. Okay, you with me? So that fixes the other end. So diatomic molecules are as covalent as you can get. Francium fluoride is as ionic as you can get. Now what about everything in the middle? All right, so what we are going to say is from 0 to 0.4, and these are delta E's. This is your difference in electronegativity here. If it's 0.4 or less, we're going to say it is roughly a covalent bond. Is it a pure covalent bond like a diatomic molecule? No, but there's not enough separation in charge or pool of those electrons to make it have a polar nature. And an example here is think of this molecule, methane. And when we do this, even though this is CH4, what I want to say is CH4 is going to have 4 hydrogens around it, but for the purposes of this chart, we're going to just look at one of these bonds, one of the 4 bonds, and say, what is its delta E? So what is carbon? Carbon is what? Carbon is 2.5. And hydrogen is? All right, you see? I told you didn't need your calculators today. Simple subtraction. We're going to subtract the one from the other one, and we get a difference of 0.4. So this is a this is a covalent molecule. A molecule held together by essentially covalent bonds. Now let's take water. H2O. And let's look at one of the bonds. Oxygen is what? 3.5. Hydrogen 2.1. 1.4. Their difference is 1.4. And so Water is made up of two hydrogen-oxygen bonds. They are polar covalent bonds, which results in a polar covalent molecule, H2O, polar molecule. Okay, so that's kind of how to use this. If you get a question that says, I'm going to react calcium with chlorine, what kind of bonding would be involved? Calcium chloride. So you're going to take the chlorine, the calcium, and look at the chlorine is 3.0, calcium is 1.0. So what kind of bonding? Ionic. It's greater than 1.9. So calcium chloride is an ionic compound. Ionic. All right. I'm not going to dwell on this. I want to get to this writing formulas. Nomenclature. And we're going to concentrate. We'll come to the end and we'll say, okay, how do you name covalent bonds? And we'll spend 10 minutes on that. We'll spend all of the rest of today and probably part of Tuesday on naming ionic compounds. And arm yourself with a couple of things. This table that I gave you. Do you have that table?
I do.
You gave it to him? So we're going to get to this. We'll work with this for a while. Just know that that table, most of the information that's on that table, you can get right off of the periodic table if you just get familiar with the fact that the alkali metals are +1s, the alkaline earths are +2, the halogens are -1, oxygen and sulfur right here, and I wouldn't even worry too much about those. Worry about oxygen and sulfur, -2. Notice that they're right on top of each other. They're in the same family, -2. And nitrogen and phosphorus in an ionic bond, in an ionic compound, would be a nitride or a phosphide, and they have a -3 charge. And carbon, don't worry about that one. It's generally not an ion. It's almost always in covalent bonds. And we'll get into the center of this table here in a little bit. Let's ignore it for right now, and let's learn how to work with these, what I would call well-behaved ions, well-behaved elements. Fluorine is always -1. You don't have to worry about exceptions to the rule. So we're right in here. Yeah, and that you can see the hydride. We've got hydrogen with a +1 and a hydride with a -1. So it depends. If it reacts with a metal, it's a hydride. How do you put the names together? The metal doesn't change its name. As an element, it's sodium. As an ion, it's sodium. It's a sodium ion. You would say sodium ion. But chlorine is the diatomic molecule, Cl2. When it forms an ion, we take off the INE and we add IDE, and you get sodium chloride. Aluminum bromide. You can see oxygen becomes oxide, sodium oxide. Sulfur becomes sulfide. All right? So you're adding an IDE. So we wouldn't say this is sodium chlorine. You won't see that on the bottles. It's the chloride ion. So that's how you put the name together. Let's see what I have here. Okay, I like this. What do I like about this slide? We're going to skip over that other one for just a second. What I like about this is that it has just ions that are kind of on one side or the other side here. So let's take this one, sodium and iodine. Determine the formula between the following elements forming an ionic compound. So to do this, we would come over here and we say, okay, sodium, what is the charge on the sodium ion? Not the electronegativity.
1.
What is its charge when it forms an ion? It loses 1 electron, plus 1. Okay? Electronegativity helps us determine, so that I can see where you're coming from. We just came off the electronegativities. That helps you decide whether it's ionic or covalent. But in determining the formula, don't use electronegativities, use the charge that it forms when it becomes an ion. So it becomes a plus 1. Iodine becomes a negative 1. All right? And what you can do here is just move the 1 over here, move this 1 over there. You would say, okay, it's Na1I1, but we don't write 1s. Just sodium iodide, NaI. If the subscript is a 1, we don't write it. It's understood. If it's other than 1, it has to be written there. And the numbers you're going to see there are 2, 3, 4, maybe a little higher than that on occasion, but generally it's 2, 3s, and 4s. Okay, now I want you to notice one other thing here, and I did say this last Tuesday, that this formula is neutral. There's no net charge in this compound. The positive charge cancels the negative charge. So if I were to add these up, that add up to 0. Plus 1 minus 1 equals 0. Okay, let's take calcium oxide. Let's look at this one. Calcium oxide. Charge on calcium, plus 2. Oxygen, or oxide ion, minus 2. So I could put the 2 there and a 2 there, and I would come up with Ca2O2. But in these formulas, what we want is the ratio of calcium ions to oxygen ions, and the lowest reducible ratio we can get from it. So a 2 to 2 ratio is 2 to 2. A 2 to 2 ratio is the same as a 1 to 1 ratio. Both of these numbers can be divided by 2 and reduced down, and so you're going to see this formula, CaO. All right, so we reduced it down. Instead of a 2 to 2, we got a 1 to 1 ratio. But notice, if we go back to their charges, plus 2 plus minus 2, net 0. Okay, let's do this one, number 4, strontium and fluorine. Strontium and fluorine. What's the charge on strontium? Plus 2. Let me get this in a place where I've got a page number over here. Strontium plus 2 minus 1. If I cross these, I get SrF2. And so if I have a plus 2 over here, plus 2 times a negative 1. I've got 2 of these, and they each have a negative 1 charge on them. 2 times negative 1, I got plus 2 minus 2 equals 0. So that formula has the same quantity of positive and negative charges in it. When the ions come together in that ratio, 1 plus 2 ion with 2 negative 1 ions. Now, in order to pick up one that we already mentioned and the bottles went around, magnesium chloride, look where magnesium is, right above, it's above strontium. So magnesium has a plus 2 ion. Chloride, now we're changing over to a different thing. It has a minus 1 ion, same as fluorine. So what happens? We get the same basic formula. Strontium fluoride, SrF2. Magnesium chloride, MgFCl2. Okay? What do you think barium bromide is going to be? Give me the formula for barium bromide. Look at strontium, barium, magnesium, they're all plus 2. Bromine, minus 1. So barium bromide is going to be what? BaBr2. You follow me? You can take any one of those with any halogen and you're going to get the same basic formula. You just got to put the right symbols there. A plus 2 ion with a negative 1 ion is going to be a 1-to-2 ratio of those ions. Has to be for this thing to come out neutral. That's what's going on here. Okay. All right, now let me give you a curveball. Not a curveball, but let's just get, I'm trying to go from simple to harder. Let's go a little bit harder. Aluminum bromide. So find aluminum, find its charge, and piece this together. Let me see what you got. Let me see. You got formulas? Okay. No. No. That's not right. Where are you getting those numbers?
Oh, wait.
Aluminum.
Oh, 3.
Okay. Right. Got one? Yes. You got a formula? What? Well, yeah, it is neutral, but what's the formula?
Oh.
The formula will be neutral. So write me the formula for A. No, that's it right there.
Okay.
That's it. That's the formula. Take that 1 out of there.
Okay.
Okay? Okay. So aluminum is group 3A. We don't have all of them in there, but aluminum is a well-behaved ion. Forms a plus 3 ion. Bromide, minus 1. So what are we going to get? AlBr3. All right? So a plus 3 plus 3 times negative 1 is neutral. This is the answer here. When you're asked for these things, give me the formula of, that's the answer. This other stuff should go on your scratch paper. All right? These bottles don't show you how they got that formula. They just have the formula. All that other stuff would clutter these labels up and get in the way. But you need to know how to piece these formulas together. Okay, let's go one more level of difficulty. Aluminum sulfide. Aluminum sulfide. And this is the way it'll come at you. It'll say, give me the formula for aluminum sulfide. What is the chemical formula for aluminum sulfide? Always start here. Write your symbols for the two elements that are involved in the compound. Write the symbols. Let me go ahead and record your formulas.
Oh, this isn't the answer though.
No, that's not the answer. You got the charges. So what's the answer? There you go. There you go. Good. Good. Let me see. You have it? Good. You got it? Very good. All right. It's good for me to check some of these. It helps me see whether you're with me. All right? Yes. All right. So we got a +3 ion forming a compound with a -2 ion. It has to be neutral. We can transfer the 2 right there and transfer the 3 down there. We get Al2S3. Now let's take a look at this. This has got a +3 charge, and there's 2 of them, +6. This has a -2 charge, and there are 3 of them, -6. You see where that's neutral? All right? It's coming out neutral. Aluminum sulfide has a ratio of 2 aluminum ions for every 3 sulfide ions. Good. All right. Now, right there, you got 6 alkali metals, 6 alkaline earth metals, these four halogens, these 2. I could throw at you about 50 different compounds, names, just with those ions. And that's why I don't want you to memorize the formulas of these. I want you to learn the system. And what I do want you to memorize is that these have +1 ions, +2 ions, -1 ions, -2 ions. Okay, let's take one more. I think we had them up here. Do barium with nitrogen. If it formed if that formed a nitride, it would be called barium nitride. Let's just get in one of those in the 3A. So let's do barium nitride. Nitrogen would have its name changed to nitride. Let's just do this one quickly. Barium is what? +2. The nitride ion is -3. So what's the formula? Ba3N2. Barium nitride. Okay. I'm sorry this jumps around so much, like I said. Okay. So now Now we want to start dealing with this middle part of the table here. And we'll look at three. I'm going to look at, well, let's see. There's going to be two transition metals, iron and copper. And then we're going to also look at tin. All right, these are not in the class that I would say well behaved. What do I mean by that is that iron can form a +2 or a +3 ion. +2 or +3. So let's just look at iron for a second. So if I come on over here, we can get iron chloride, or we can get iron chloride. In this particular iron chloride, it's a +2 iron. Chloride is always -1. So in this iron chloride, it's a +3 ion. So I can't call these iron chloride. I can't just stop there. I can't say, go get me a bottle of iron chloride. You'd go over there and they would look at you and they say, which iron chloride do you want? He didn't tell me. Well, he should have told you. Iron 2 chloride or iron 3 chloride. Follow me? This is called iron 2 chloride. And this is called iron 3 chloride. Roman numerals here. We're using Roman numerals. Iron 2 or iron 3. And the 2, the Roman numeral, refers to the charge that is on the iron. It does show up over here as 2 chlorides, but the name is telling you the iron is a +2 iron. You follow me? And let me show you. Let me drive that point home. Let's look at iron 2 oxide. What is the formula for iron 2 oxide? So to do that, I know the symbol for iron is Fe. I know the symbol for the oxide ion is O. What is the charge on the iron? +2. Where are we getting that? Right from this. This is telling us this, nothing else. What's the charge on the oxygen? What's the formula for iron 2 oxide? FeO. There's no 2 in the formula. You follow me? The 2 isn't telling you anything about the numbers in the formula. It's telling you the charge on the iron. Because iron can have 2 different charges.
Is it only iron?
Pardon me?
Is it only iron?
Well, whenever you see a Roman numeral, then you're dealing with an element that can have 2 different charges, and it's telling you what charge it has. We'll look at another example. Here's iron 3 oxide. What's the formula for iron 3 oxide? We got an FeO. What's the charge on the iron? +3. What's the charge on the oxide? -2. It doesn't change. Oxide is always -2. And notice here, we're going to get a 2 down in there and a 3 down in there. Fe2O3 is iron 3 oxide. Okay? So, let's go back over this slide. So you see here, you can there's your iron 2 chloride, FeCl2, iron 3 chloride, FeCl3. Copper can be a +1 or a +2. So copper 1 oxide, look at that. Copper 1 oxide is Cu2O. This Roman numeral 1 is telling us that's a +1. But this is a -2. So you get a 2 in the formula. Copper 2 oxide is just like iron 2 oxide, CuO. All right, in tin, look at down here in tin. Tin can be a +2 ion or a +4 ion. Tin 2 oxide, tin 4 oxide. So tin 2, a +2 tin, a -2. Okay. All right. The waters get a little. Yeah, Luke.
So I got that the Roman numbers tell you for that metal. Like, how do we know that 10 would be a 2 or 5, 2 or 4?
Okay. On these 3 elements, you're going to need to learn that. Okay. I'm not way back there. There was a whole bunch in the transition metals, and I'm just saying learn these 3. Learn that iron can be +2 or 3, copper can be +1 or 2, and tin can be +2 or 4. So this slide, you should learn this slide. What don't you have to memorize? See back here, there was a whole bunch of other examples in here. Is this? Yeah, there we go. So there's your copper 1 and 2, your iron 2 and 3, and we should have had the tin 2 and 4 in here. And that's, I'm just saying, learn, just learn, where is tin? It's down right here. So learn these. But if you came across chromium, look at this one right here. I want you to learn 3 of them so that if you ever see a Roman numeral in a name, you know what that Roman numeral is telling you. So you can come across a chromium compound. It says chromium 6 chloride. You go, I wonder what's Roman numeral 6. So it's chromium. I'm going to move off of this because there's one other thing I want to touch on. If you got a 6 in there, you say, what's that? There's a Roman numeral 6 in this name. That means it's a +6 chromium. It's a +6. But you don't have to memorize that. Just key in on the iron, the copper, and the tin. And you can't figure it out. You just have to kind of know that. You just have to know that that's how they behave. Okay, now let's get to one other key chart so that you could start understanding what to do with that. That's this chart. There are such things as polyatomic anions and cations. They're very common. These are very common. This thing has a mind of its own. I think I better reload this thing. Let's see, which one would you have heard the most about? Probably carbonates. Carbonates. What is a carbonate? There is sodium carbonate, magnesium carbonate, aluminum carbonate, barium carbonate, carbonate, calcium carbonate. There's a lot of calcium carbonate. The water trickling down through our sandstone and everything else around here is going down through calcium carbonate. That's why our water's hard. It picks up a little bit of calcium carbonate in the water. Calcium carbonate. Carbonate is always CO3 with a -2 charge. So carbonate, CO3, and it carries a -2 charge. It is a polyatomic anion. So if you ever see carbonate in the name, that's what they're talking about. Baking soda is sodium carbonate and sodium bicarbonate. Those two. So there's the carbonate and the bicarbonate. Well, let's look at sodium carbonate. And let's write a formula for sodium carbonate. I would write the symbol for the metal. I would write the formula of the anion, the polyatomic anion. That's a carbon and 3 oxygens that are bound together and have a -2 charge. This has a -2 charge. This has a +1 charge. So if it's like that, I'm going to transfer a 2 right there, and I'm going to think of a 1 here. And I'm going to get the formula Na2CO3, sodium carbonate. Let's pick on carbonates for a little bit. Let's do magnesium. Let's do magnesium carbonate. What is the formula of magnesium carbonate? Okay, magnesium is Mg, carbonate is CO3, and make sure you write a big O. C with a little o is cobalt. Okay? Don't get that mixed up. That in a chemical formula, you're telling me it's cobalt in there. C and an O is carbonate. -2 charge, +2 charge. So what's the formula of magnesium carbonate? MgCO3. Okay, let's get a little bit harder. Aluminum carbonate. AlCO3 +3 -2. So the 2 is going to come into here, right? So we're going to get an Al2. The 3 is going to go over here. But we are not going to do this. That's 33 oxygens and 1 carbon. That's not 3 carbonates. What we are going to do is now put a parenthesis around the polyatomic ion and write a 3 outside the parentheses. So the formula of that is Al2 parentheses CO3 parentheses 3. And let's just kind of track with this. So 2 times a +3 is +6. 3 times a -2, again, is a -6. All right? We're using the same logic. We're using the same pattern, but if it is polyatomic, if there's more than one atom in this ion, then you need parentheses around it if you have a subscript after it. You can see up here, magnesium carbonate, I didn't use parentheses. Why? There's only 1 carbonate. I don't need parentheses. I only need the parentheses when there's more than 1. Okay, now you're heading off into the weekend. You've got these 4 tables. You should start committing these to memory. If you want to put these on 3x5 cards, you know, carbonate on one side of the card, CO3 with a -2 charge on the other side. Look at what sulfate is, SO4 -2. There is a practice quiz. Have you seen the practice quiz on Canvas? Go to quizzes. And you will find a naming and formulas practice quiz. It's no grade, it's not graded, but let me tell you this. That quiz is going to be put up into the testing center, and Tuesday, Wednesday, and Thursday of next week, you can go in there anytime you want to and take that quiz. And it's going to go into your quiz section of your grading, and it's not going to be dropped. All right, I said I will drop your 4 lowest grades. That one won't be dropped. It's a required quiz. It's not going to be any different from that practice quiz. The practice quiz gives you 20, randomly picks 20 compounds. 10 of them, it tells you to name them. 10 of them, it tells you to write the formulas.
You said next week starting what day?
Tuesday, Wednesday, and Thursday. So you should do that practice quiz 2 or 3 times this weekend. And you don't want to go do that quiz up there until you're getting an 18 out of 20 on the practice. And then you'll know you're going to get 18 out of 20 on that or more, okay? So start doing that practice quiz. It's just driving you through naming and writing these formulas. I know I'm holding you, but if the formula is MgCl2, I like them like that. I think on that quiz, you're going to have to write them like this, okay? So just know that is that. You can't put subscripts into the fields. But this isn't the way to write it on a written test or exam. This is the way to write it. So I'm not trying to teach you the wrong way. It's just not easy to format a subscript. All right? Okay. And if it needs parentheses, it needs parentheses. I'll count everybody here today. I didn't, but I think everybody was here.